my pleasure to introduce Yeshaiahu Fainman, all the time my friend and also a graduate from the Dept in Israel. And he's, here let me give a big introduction that he's been at University of Michigan before becoming a professor at UCSD, University of California, San Diego, since 1990, he's been there. And he has had numerous contributions in femtosecond pulse processing, nanophotonics, diffractive optics, and whatnot. He's everywhere. So I'll let him speak today. Thank you, Shaya.
Thank you, Rafi. I hope you can hear me. If not, just yell back. If you don't hear, I will yell back that you hear. So I'll talk a little bit on nanophotonics for information systems, some of the work that we have been pursuing for quite a while. I'm looking back. We started early 90s to look into this deeply subwavelength structures. At that time, I never would even bother to say it's nano, but then it became a buzzword. I jumped on the wagon, and here we go. It became nanophotonics. So before I go with some real optics results, I'd like to make a brief introduction for motivation behind this work. And the motivation that drew us into it was going back in a couple of problems which I will highlight. The first problem is that computing, and this is not exaggerated, this is actually taken from Sandia Labs' website, that a parallel computer today consumes more than 100 megawatts of power, which corresponds to a small power station. So it's nothing really exaggerated here. And today's computer industry looking at multi-core processors, and as the clock cycle goes faster and faster, to drive the electrical wires becomes harder and harder. And some point it is envisioned that we will be able to use optical communications as close to the chip as possible, especially for multi-core processor in problems of memory access. It became a real problem today, and we are working in a very close collaboration with computer industry, specifically Sun Microsystems, on a reasonably big project. Of course, we are a small player in this big project, where they are trying to bring the optical communication closer to the chip. The second class of problems that would benefit from optical communications are problems in data centers. Data centers, in contrast to parallel computers, are more network-centric, but as the time goes on, we will see that these two technologies will merge together, and what people are calling or envisioning in the future will exist as cloud computing. So there are few issues that you can identify, and here is the issue that actually looks pretty bad. These are the wires wiring modern data center. It's called sometimes a yellow wall. Looks pretty bad, but that's not the problem. Okay, you can just pay and do it. The real problems are listed here. One of them is the scalability. They don't want to rebuild every time a new data center. They want to extend the existing. So the scalability is an important issue to address. They dissipate a lot of power in communications. In fact, with my colleagues from computer science department, he estimated that about 15% of dissipated power could be saved if you would utilize optical communication. And consequently, this is very expensive, and that's why data centers that Google builds are next to the Niagara Falls. Why? The energy is very inexpensive there. Okay. So everybody knows this. I'm not going to go through it. Optics is great for many different reasons. It proved itself in some applications, like those long-distance communication. Everybody knows without fibers, we wouldn't have internet at the speed we have it. There are a couple of unique features that optics has. Again, the impedance matching for power-efficient connections. That's unique for this chip-scale interconnection, where the RF communication over wire would cause much more impedance mismatch and thereby power dissipation. Optics brings parallelism, which is very essential for these data centers especially. And they can be miniaturized, and plus various transformations. You probably have seen all of this in different contents, so I will not dwell on it. But miniaturization is very interesting and important. So we've done that, as Rafi was mentioning. I've been around for a while. So here are a couple of highlights what we have been doing for so many years. So this was one of the papers that we've started in photorefractives. We did some logic. We built some complex systems to make optical filters. And these are real systems on optical table. This was a real system that actually did a computation, matrix inversion. It worked sometimes. Okay, so then we went on and said, well, forget about that. Especially, it was very useful technology when the digital computers were operating in kilobits per second. As computers got faster and faster, we had no advantage, so we went on and said, okay, let's go do some ultra-fast. So we built the first optical oscilloscope that was visualizing phenomena on sub-100 femtosecond scale. We continued to perform various transformations. I'm not going to dwell on it, but at the same time, we also built networks. And these multi-stage interconnection networks, for some reason, the computer science faculty that works on data centers, they came back on them. So I put this slide purposely, that all this was done. We knew how to do it. Not very functional. And why is that? Okay. So all the know-how is there. What is not there is the technology. So the technology was very expensive because we used semi-manual integration and very difficult integrating optics with electronics. Recently, as recent as mid-80s, people started to use lithography and microfabrication tools to make optical functionalities. And first example was the binary optics or diffractive optical elements that were pioneered at MIT Lincoln Labs back in mid-80s, I believe. And since then, actually, people started to think more and more in the direction of using microfabrication to make optical components and implement various optical functionalities. Now, at this point in time, we believe that using the advanced lithography tools, we can control geometry, we can control composition in the geometry to implement or realize materials, which sometimes we call, again, as a buzzword, metamaterials, materials that are not existing in nature, with properties that we need for realization of these different systems. So I went one day on a Sunday afternoon to look what is the SRC roadmap predicts on lithography. This was a few years ago. And they say 16 nanometer by 2020 about. That's telecommunication wavelengths 100 times smaller. So then you can actually engineer any materials you want if you can achieve this resolution and create materials with properties that uniquely suited for an application of your desire. So what we did in early 90s when we first thought of this deeply sub-wavelength structures, that it's a very difficult problem. It was difficult then, it is difficult now. Because what you need is have design tools. You need to be able to fabricate this composite materials, if you like, and you need to develop tools for characterization of these nanostructures and devices. So what we actually, our objective mainly was to exploit near-field optical system science. Really, maybe there is something new dealing with near-field interactions where you look at deeply sub-wavelengths, polarizability of the media, and you create properties and functionalities that are necessary for various applications. So I want now to very briefly go through this diagram. This was something relevant to diffractive optics, and this was when the atomic subsystems were separated by long distances. So you could use scalar diffraction theory to design this diffractive optical elements. Then people started to look at vectorial properties as well. But what we are primarily interested in is this case when the atomic subsystems are brought very closely to each other. When they cannot be treated independently, they become electromagnetically coupled, and consequently, to solve or to design structures based on this type of atomic subsystems, you need to go and use Maxwell equations, which is not a simple thing. Something that is exciting for you probably, to look at quantum interaction as well, and this may be extremely interesting direction in the future. I'm not going to address that aspect of interaction of atomic scale subsystems. So we went and wrote our own codes back 15 years ago. Today we use RSoft and COMSOL standard modeling tools, which are commercially available. Some of them are good, some of them are limited, but need to use them with some finesse. Sometimes there are some issues, but overall they are very good. We developed lots of different recipes fabricating this nanoscale photonic structures, and here is an example. This periodic sidewall of a waveguide is modulated with amplitude on the order of 50 nanometer. We made microring resonators, crystals, and some resonant structures. This is something I need to put some propaganda in every talk I give for my dean to be happy. This is the new building, California Institute of Technology and Information Technology. This lower part is then called Nano 3. Nanofabrication facility has electron beam writers, etching machines, deposition machine, everything you need for microfabrication. Everything I will be talking about was done in this facility. And for characterization, of course, we have to develop our own tools, and we started to develop this tool in late 90s. Something unique to this near field scanning optical microscope that it uses heterodyne detection, which provides you a detection gain due to the mixing process that is about 10,000 times higher sensitivity than the commercial products that don't use the heterodyne detection. So that's a very interesting wrinkle that we did. And basically we bought Ensom from Nanonics, all the electronic drivers and components, but all the detection system around was homemade in the lab by our grad students. And the machine gives us 4 images. One image is the topography. The tip has an AFM. The detected heterodyne signal provides near field amplitude and phase that we extract from the detection system. And we also put a fiber at the output of the functional device, and as the tip is being scanned, we monitor the output. If the tip does not affect the device, means it doesn't interact. And usually it does interact. It's like at quantum mechanics, you measure it, you perturb the system. So that's the same thing here, and it's very handy to have these images too. Of course, I want to acknowledge before the end of the talk my students, colleagues, and some of the funding agencies without whom we wouldn't be able to build all these nice devices. So now I'll switch gears to some of the current work that we have been doing. It's summarized here again. Use lithography, very simple. Use lithography to make optical functional devices as much as possible. If possible, do it CMOS compatible, so it becomes practical eventually. So that's our main objective. So what I will do is go very briefly through inhomogeneous materials, quantum nanowires, whatever we call them. I'll show you some results on our most recent result on sub-wavelengths metal insulator semiconductor laser that operates at room temperature. Talk briefly on plasmonics and silicon photonic plasmonic antenna and broadband ENSOM, but it might be that I will jump through slides to talk about broadband ENSOM as most recent result that we did. I want to leave like 5-10 minutes talking about. So if I will be running over, I'll skip something along the way. So the journey started, as I said, in early 90s. In 95, we published work on form birefringence, which is nothing new. It's in Born and Wolf book. It was actually invented by a German scientist in 1895. And the idea is very simple. You take periodic structure with very high contrast of dielectric constant. And if you introduce field propagating across, if it's T polarized, the tangential E field is continuous, so you see some average index or average dielectric constant. Whereas if you are TM polarized, the electrical displacement, the normal component is continuous, so your field is sitting in the low index area or low dielectric constant. So what you see effectively very low dielectric constant. So the birefringence is huge. So you created artificially a film of a uniaxial crystal. And the birefringence that we estimated is about 5-7 times larger than the largest available in natural crystals, and it actually is for silicon in air interface. If you control the duty cycle, you can control the amount of birefringence. So there are a few degrees of freedom you can use in engineering the material. We used it in many different applications. One is polarization sensitive computer hologram, which has two independent impulse responses for two orthogonal polarizations. It was a spectral reflectivity that was devised that was anisotropic. It was actually first photonic crystal in 2D that was ever built. It was done with the same scheme. It was a joint work with Axel Scherer and Eli Jablonovich. And we also built some near-field resonator to build a modulator. I'm not going to bore you with old stuff. I'll show you some new things that we have been working more recently. And one of them is what I call materials with space variant polarizability, or we call it sometimes free space optics on a chip. So you know in free space you have continuum of modes. In a guided structure you have discrete modes. So here what I'm basically saying, I have discrete modes in the vertical direction. I'm looking at a silicon slab of 250 nanometer on a silicon dioxide layer on a silicon wafer. And in the transverse direction, you can excite any free space modes. So the idea here is very simple. We take a periodic structure of 150 nanometer and we change the duty cycle from left to right. We increase the amount of silicon and decrease the amount of air, which we fill in with silicon dioxide overlay later. So the index is varying linearly and nothing surprising. You shoot a beam in the simulation and it will bend like in a prism. Now something interesting happens when I do the same thing, but for a period of 300 nanometer. What you will get is this snake-like propagation. And this is something very interesting. You can explain it hand-wavy. basically what happens is the following. It bends, and at some angle at this particular wavelength or frequency, you satisfy a Bragg matching condition. So it reflects off as a volume grating. So it propagates now in the opposite direction towards the lower index, and then at some value of the index, you will satisfy the total internal reflection condition, and you will bend back. So the beam propagates like that, snake-like trajectory. And what is it good for, you can say? We don't really know. It's just interesting. One thought is build a wavelengths division demultiplexer. Different wavelengths would take different trajectories, and then maybe you can design that at the output they will appear at different locations, for example. And we actually did some simulation. It looks like it. You can do some optimization and design like that. We actually made this structure shown here with SEM micrograph. This is Ansom image of the amplitude. This is a zoom-in version, amplitude and phase, and you clearly see that as you bend the beam, you should see a higher index. You see higher index, the phase fronts should become denser and denser. That's what you clearly see here, that the period of the fringes is decreasing as the index increases. Well, we applied the same kind of ideas to build something useful. This we didn't know what it's good for. This is good for matching modes of different waveguides. So you can engineer the mode matching any way you like by creating, I would say, you can think of it as a graded index lens, for example, the simplest example. So I would make a structure that would take the diverging beam coming out of a waveguide into a silicon slab, and then this lensing structure would focus the beam back into the output waveguide, as an example of experiment. This is the cartoon, what I just said, and this is the top view of a fabricated structure, and this is a side view showing that we can get features of about 100 nanometer. And this actually is the summary of the experimental measurements of the whole structure. This is zoom version of the Ansom image of the amplitude in the area of the lensing structure. And this is the phase image, and you clearly can see that the curve 2 is curved, it's diverging. Then the lens starts bending the wavefront back into the focal point. So you straighten the wavefront, then the wavefront becomes converging, and when it focuses, you get this, I believe it's 5, you get, again, flat phase wavefront. So that was nice. Now I'd like to switch to the next subtopic on what we call photonic nanowires. And the idea is very simple. If everybody knows that in integrated optics, people make Bragg reflectors. And usually it's done on a waveguide. On the top of the waveguide, they make a periodic structure and becomes a Bragg reflector. Now, in the past, it was not possible. Now, as lithography became better and better, you can now, instead of having two-step process, you can do one-step process. And actually, like I was saying, I want to use lithography as a pen, writing something. So I want to use lithography to write this periodic structure. And if I don't want it periodic, I'll make a non-periodic. So I can write anything I want. So that's basically the idea, and it sort of compares favorably with nanowires. There is a lot of research and activity in nanowires, which is great. But I think this I like very much because I can engineer, I can write, I can put them together. If I grow nanowires, then I want to make a device. I need to find it, I need to drug it, I need to position it in a specific location. It's very difficult technologically. So that's what we have been doing. And here are a couple of examples of structures that we've made. This example is a channel waveguide or photonic wire with sidewall modulation of 50 nanometer. And here in the middle, so if I don't do anything, you can think of it a one-dimensional photonic crystal. Now in the middle, I say, okay, I'll make quarter wave offset. I'll make a mistake. So I introduce a defect in the photonic crystal. So what would I expect? I would expect a wide stop band because the effective index of the modulated structure and the narrow region is smaller than in the wide region. So consequently, you get effective index modulation, and if the difference is large, I will get an appreciable stop band. And that's what you get. This is measured data, by the way, 19 nanometer. In the middle, because of my defect, I introduced a pass band. And the pass band was about 6 angstrom bandwidth, which corresponds to a Q of 2600, which is very good result. So then we went on and said, okay, for telecommunication application, what you want to do is to build, basically it's nothing else but a filter. So you want either to use it as a modulator or you want to use it as a photodetector if you put here some germanium to absorb the 1550. Or you can use some design as a filter. One wavelength goes through, the rest reflects. Okay? The only difficulty is you want to operate in a C-band, which is much wider than 19 nanometers. So we had a little bit of difficulty. So we said, okay, to get wider stop band, you need to make the contrast higher. To make contrast higher, you modulate more. So that's what we did here. We modulated a lot. As you modulate a lot, you certainly get wider stop band, but you also get much wider pass band, which is not good. Why is that? Scattering loss. So the Q goes down as you scatter light on this deeply modulated structure. So we never give up, and we came up with a different design of a pair of simple quantum wires with a Bragg modulation on the sidewalls. So if you look at one of them, of width W1, you will reflect any wavelengths going through will go through, except wavelengths that satisfies Bragg matching conditions. So let's say lambda 1, 2 beta 1 of lambda 1 equal 2 pi over lambda grating, lambda 1 will reflect. Same would apply for the waveguide 2, but we make it different widths. So the beta 2, the propagation constant, is different from beta 1. So it satisfies the same Bragg matching condition, but for lambda 2, a different wavelengths. So I'm now having a window that I can work in between lambda 1 and lambda 2. And guess what? You can design this window close to 100 nanometer almost by varying the widths. Now, you can also bring them very close to each other, so they are electromagnetically coupled. They are coupled gratings. So there is a cross-coupling Bragg matching condition, which is beta 1 of lambda drop plus beta 2 lambda drop satisfied. That's the lambda that from waveguide 1 will be coupled to waveguide 2 and reflected to the output to the port 2. So that's basically the idea behind. And this is the summary of the design. You satisfy the 3 Bragg matching condition. You determine coupling coefficient by using some coupled mode analysis. You estimate. And this is controlled by the modulation and the distance between the waveguides. And you determine the lengths to get good extinction ratio. So we actually made such structure. This is a microscope image. This is the zoom-in SEM. Shows you that the two waveguides are indeed very different in widths, 550 and 430. And the measured data was, the design was to drop something between around 1550. And you can see the FDTD simulation and the measured data in reasonably good agreement. This is something that I think I wanted to skip, but I decided last minute to change. What happens if I make the periodic Bragg structure aperiodic? I just chirp it. I make a chirp Bragg grating. Now the chirp Bragg grating can be designed to have a flat top and a linear dispersive relation. Now depending on the sign of the chirp, which I determine when I write with the pen, I go from lower modulation to higher or higher to lower. I control the normal or anomalous dispersion compensation. So that's basically summarized here. These are the chirps we used in the design. These are expected group velocity dispersion and measured group velocity dispersion. And you clearly can see that you can make it negative and positive by just flipping the sign of the chirp. So that's something that can be very useful structure for integration on a chip in front of the receiver, for instance. You could compensate for dispersion. Of course, the numbers need to be large if you want to deal with long communication distances. But remember, there are many applications where you don't need to go very long distances as well. So, but the speed goes up. So there is limitation in the sidewall modulation. Never mind, I keep preaching lithography is great. It's true, it's great, but it's still limited. 50 nanometer is already challenging. So what if I need coupling coefficient very small, corresponding to modulation of, say, 10 nanometer? What would I do? So that's basically what motivated our work on this new sidewall modulation, which we call cladding modulation. You basically say, okay, make a straight waveguide and introduce cylindrical bumps of silicon in the cladding. And make them small enough so that you don't hit a whispering gallery mode resonance in them. So they are basically very deeply in sub-wavelengths. And then control the distance where the bumps are. The longer the distance, the smaller the overlap with the evanescent tail of the mode in the waveguide. Consequently, your coupling coefficient is small. The smaller the D, the larger the coupling coefficient. And similarly, the low modulation gives you much narrower bandwidths, as expected. So we made a device like that, shown here, and for two specific designs of the 200 nanometer and 50 nanometer, low modulation, high modulation, narrower stop band, higher stop band, larger stop band. So that's nothing not expected. So I'd like now to brag a little bit about this laser work that we've done. It's really was something that for some reason we wanted to create a laser that is smaller than the wavelengths of light, for reasons that we always are being criticized that, oh, and how do I get a source into the silicon photonics? I need a fiber or I need a laser, and then there are a few ideas, but it's always large. It doesn't scale very well. So that was basically a challenge that we wanted to investigate. And also I mentioned enough times that these small devices, when you bring them close to each other, they start getting coupled electromagnetically. So you can't have close proximity between devices. So you want now to make sure that this laser is isolated from the surrounding. So it's small and isolated. So that's a challenge, and we looked at possible technologies. Here is a photonic crystal laser, where you take a photonic crystal lattice, say in a membrane, and you make a defect and it lasers there. But it's a little bit cheating, because the mode extends quite a few periods away from the defect. Same with the VCSELs that are pretty small, but the Bragg reflectors are really high, large in scale. So the closest that comes is the whispering gallery mode resonator, which is nothing else but a disk of gain media. And you excite a whispering gallery mode in this resonator. Now, on one hand, you can't say that the mode is confined, because it still has the evanescent tail of the whispering gallery mode. Also, the smaller it gets, you introduce larger radiative losses. So your gain media has to compensate for the radiative losses. Additionally, as you make it smaller, the modal overlap with the gain media gets smaller and smaller. So you need again to increase the threshold gain. So that's a nice idea, but not trivial. You have to use it. So another problem is that if you take this guy, designed for 1550, and you bring another laser close to it, say 120 nanometer apart, it shifts in wavelengths because they are now a new system, new resonator. Okay, so they talk to each other. a few years back, we looked in our group at how to confine light, and this is usually done with plasmons. Now, plasmons are losses, so we came up with an idea. What if we put surface plasmon polariton fields on top of a gain media, which flips the sign of the imaginary part of the dielectric constant? And we did some studies, and there are some interesting opportunities, and that actually triggered us that metals are good. They isolate the device. That's a good part. But the bad part, they are very lossy. And here is a analysis of a disk made of semiconductor, about 920 nanometer disk with 480 nanometer thickness. And this is, if the disk is in air, you get a Q of 875. And the mode is M4 here. Then you put a metal to isolate. So, of course, the mode is squeezed inside the resonator, so M3 is now resonant. And the Q drops to 183. Now, you can excite also the plasmonic mode. It's terrible. Q is 36, so your gain requirement is much, much higher. So the plasmonic modes are challenging to use in this type of lasers. So we came with some type of a new resonator design, which is, we call it metal dielectric semiconductor composite resonator. And the red is the semiconductor. This greenish is the low dielectric constant silicon dioxide and metal on the sides. So in the vertical direction, this is low index, high index. So whatever mode is resonant is propagating. It's like a coax. Think of it as a coax. Now here, low index, and the diameter is small, you are in a cutoff. So it acts as a reflector. So the same at the bottom. Now, so that's good. So we basically confined the mode and created a resonator here. It's like you can think of it as a Fabry-Perot resonator. Now, on the sides, though, you have, if you put metal directly on the gain media, without what we call shield, you will have very high loss due to absorption in the metal. Now, if you put this shield very thick, you have very little mode overlap with the gain media. So also not very good. So there must be an optimum. And of course, we found the optimum that for a given radius, you find an optimum 80 nanometer shield for the total of 300 nanometer radius of the device. So we went up and made the design of the lasers, different sizes. This is the SEM picture of the result of lithography. This is after etch. So we use a slab of indium gallium arsenide phosphide on indium phosphide substrate. So this is the pedestal. From here to here is indium phosphide. This is the gain media, indium gallium arsenide phosphide. Then we coat it with silicon dioxide, then sputter aluminum, then transfer it on a glass substrate with some glue, and remove the indium phosphide substrate altogether up to here. So that's what you see here. It's the top view now, whatever is glued to a glass substrate. And this is the top view, and this yellow helps you to see the shadow of the silicon dioxide shield around the semiconductor. This is just semiconductor. And this is the cartoon explaining the whole structure. And in the testing, we tested quite a few different sizes of the resonant frequency of the mode that requires minimal gain is changing, and we are still investigating how to better control the fabrication steps. But it certainly shows very clear light-light curve where it is a laser. It's not amplified spontaneous emission. And the size of the laser is well below the wavelengths of light at which it emits in all 3 dimensions. And it operates at room temperature, which is very new. Now, I'd like to talk a little bit about the plasmonics in the content of integration, again, of photonics, but this time with microfluidics. motivated primarily by biology applications. This was part of Center for Optofluidic Integration that we had for 4-5 years, expired last December, and we are trying to get it back up and running once DARPA is becoming rich again. So at this point in time, I will show you some work that we have been doing under this program. And the motivation was primarily, why use plasmons? Depends for what application. Many applications say, if I want to build a modulator for telecom, the losses are intolerable and probably is not a good idea to use plasmons. But for biosensing, we can afford the losses. Now, why would I go, what is the advantage of having a plasmonic field versus optical field, say guided wave? That if I do surface chemistry, on the surface of a dielectric, I deal with evanescent tail. On the metal, the physics is different. I deal with the maximum of the field. So that's the biggest advantage. Now, additionally, plasmons enable us to localize the optical modes to very small volumes. And I'll show a couple of examples of that. Well, actually, I'll go through this very quickly. We've done studies of nanohole arrays. When Ebbison published the paper in the late 90s, we tried to understand it too, because there was a lot of controversy. So we did quite a bit of studies. I don't have time to go into it, but we understood a couple of things which made it very attractive for biochemical sensing application, and we actually use it quite a bit. We also developed what we called surface plasmon polariton Fourier plasmonics, whatever the buzzword means. It appears that you can do Fourier optics with surface waves, and you can make a diffractive structure, you can make a photonic crystal, you can make actually something much more exciting that I will highlight, is a silicon waveguide with a metal particle that localizes the field into the gap of this metal particle. So let me go away with this stuff up to here. So this is basically a summary of this work, and what our motivation was to combine few effects into one structure. One is the Mies resonance. So you take a metal disk and you can excite a resonance. So if I introduce light on a metal disk, I will excite a resonant mode of this disk. Now, if I have a metal taper, I create adiabatically focusing of the plasmon fields. Now, it is well known also that from antenna theory, if you take a split antenna, all the field is sitting in the gap. So if you make a nano antenna with a gap, all the field will localize in the gap of the split antenna. So what we did is added all three phenomena into one structure. So we suck the power from the waveguide into the resonator, and then we focus and localize it into the antenna split. So that's basically a cartoon of the experiment. This is the SEM summary of the device. So actually it was first demonstration of silicon photonics integrated with plasmonic type focusing antenna. And the way we did it is first did fabrication of silicon waveguide, deposited a disk of metal, and then went to a focused ion beam machine to cut out this nanocrescent moon structure. Then we measured it using ENSOM in the near field. Unfortunately, the tip was 50 to 100 nanometer, and we were anticipating to detect something by design close to 25 nanometer localization. Didn't work directly. This is the raw image, but we did a little bit of image processing, inverse filtering. It's challenging. It's still questionable how well we did it, because there is a problem. The tip has metal. When you scan metal on this nanoparticle, there is a coupling between the metal and the plasmon. And you couple light as you scan your metal tip. So it's a very complicated problem. We tried very hard to model the tip together with the crescent to estimate the impulse response and to deconvolve with it. It is challenging. That's all I'm going to say. However, whatever we got conservatively is corresponding to 75 nanometer. And this is, again, localization of optical field to about lambda 0 over 20, lambda 0 in vacuum. Of course, you can say, okay, in silicon, I can do lambda over, say, 2n. So it's lambda over, 7 or so. Well, still a little bit better. I'd like now to talk a little bit, few minutes, on our most recent work when we took our heterodynensom and changed the source. We used monochromatic sources. We used ultra-short pulse. This time, we basically used a super LED. And this is a cartoon of the diagram of the scheme of the ensom. We use super LED, 2 arms, reference and signal arm. It's a Mach-Zehnder arrangement, and the light is coupled into the photonic structure, and then with the tip we pick up the evanescent field, and we beat it with the reference signal. So that's what we've done with monochromatic source. Now it's a broadband source. Of course, what we had to do is make sure that the dispersion in reference arm and signal arm till the illumination point is equal. So that was challenging, but we did that. So in the experiment, what we do is we take the tip and we first position it at the very input of the waveguide that we want to analyze dispersive properties or what have you. And then we measure the, in this case, autocorrelation function of the source. Okay. So here are some results. So this is the spectrum of the superluminescent diode with center wavelengths of 1539, and the width is about 44 nanometer. So if you take power spectrum, do a Fourier transform, you get what? Autocorrelation. And this is what you get, 178 femtosecond. Now, if I go back and I position my tip here, and I change the delay in my delay line in the reference arm, I will again measure the autocorrelation, assuming that the dispersive properties are compensated in both arms. So from the measurement, we get 180. From the calculation, from the spectrum, we get 178. It's pretty close. So then we went on and did something else. We don't change the delay line, but we scan the tip now. So as you scan the tip, you create again a autocorrelation function of whatever the distribution you have, but now in space. So you scan it, it's like exactly as the result you would get with ultra-short pulse, exactly the same. And it costs a couple of $1,000 versus a couple of hundreds of $1,000s. So that's very useful. And you can also, from the phase image, you can estimate the effective index, which is a very useful measurement, measured effective index, not calculated. And also another advantage is that with the broadband source, you don't see the speckle noise because it's being averaged. Whereas here with monochromatic illumination, you see a lot of speckle noise. So we used it to track a pulse as it propagates in a simple waveguide. So you go and change the delay. You start with this delay in the reference arm, and then you increase the delay and the pulse as if it propagates, right? And goes away. And you go and plot it. This is the position of the pulse as a function of the delay. Green is short delay. Yellow is longer delay. Then you plot peak position versus delay, and you get the slope corresponding to your group velocity. And then you estimate the group index and compare to beam propagation result. You find them in reasonable agreement. we still are working on it. It's just beginning of using this system. And I think I will just leave the summary, and thank you for the attention.
You mentioned in the near field experiment that you did the deconvolution.
Mm-hmm.
Is it shifted variant? You can actually
No. It's space variant.
Right.
In fact, we used space variant too, because we did some estimate of basically, if you look at the simulation results, you can see that there is some dependence on the image you are measuring, because the tip is basically, you can think as a metal cylinder with a hole, and that would be at least rotationally invariant. But even the moon is not really rotationally invariant. So that, yes, the answer is a space variant impulse response. And it's challenging to figure it out numerically.
I have a question about the waveguide with the little discs along the side. It seems like, and this question might apply to all these devices, the distance that you want to control is very exponentially sensitive. So you'd really like to precisely control that. But with these kind of lithographic techniques, you have some quantization of the distance. You can only move by one minimum feature size. What happens if you want to move by some amount that's a t fraction of that, or in order to control, to design the device the way you want it? What do you do?
Well, it's a very good question. Lithography has its own limitations. Now, resolution in writing is not necessarily the same as resolution in the positioning. So that's basically, we are counting on the very accurate positioning. And to give you a fair answer, it will be a problem if you write long. I'll give you an example. Our e-beam machine, we had very hard time to reproduce some results because of the stitching. So we conducted an experiment. Writing a waveguide, moving the stage, stitching. The stage is perfect, interferometric alignment, and not a problem. For some reason, we get very large stitching errors. So we shoot an e-beam for an hour and a half to the same spot. We got a few hundred nanometers. So there is a positioning error that you need to realign every time. But to tell you the truth, Kevin, I don't have a solution to it, but I'm sure in lithography business, people solve this problem, because otherwise we wouldn't have this 45 nanometer wires today in current nanofabrication, and projections to 16 nanometers. As a fix, a solution, and we are working on it, you could introduce more bumps and remove some of them to fix it on the spot. It's like trimming. Okay, so that's basically something we are working on to make sure that we can fabricate a device, and if it doesn't perform well, we see the SEM, we can go and fix it. But then it's tedious process. I mean, as a research, it's an interesting problem, but as a manufacturer, probably no one is going to do it, because we will go into FIB and correct what we can see that needs a correction, right? So that it's not. I personally don't feel it will be a good technology to fix problems. You want to not to have the problem. So lithography probably is the answer, and I'm not an expert to give you a better answer.
What is the limit on the size on your nanolaser device, and what determines the limit, and how close are you
Well, it's a very good question, tricky question. It depends what is the maximum gain I can get from the semiconductor. Current designs assume realistic numbers at room temperature. In fact, we went to lower temperature. We do everything in cryogenic right now. So we can drop the size at cryogenic temperatures, factor of 2 at least. But to be practical, it has to operate at room temperature, or maybe cooled, but not to liquid nitrogen. So it's a good question, and it depends what quality of material gain media I get, because that's basically what determines the size of the laser is the gain mode overlap. If you have more gain, you can overlap less. Use metals with finesse, maybe better metals. We talked about possible use of silver, which we are investigating. Silver seems better metal in terms of losses, less lossy metal than aluminum. Haven't seen it yet. So, and numbers from handbooks are not necessarily accurate yet. So
I mean, those were the nano lasers were pretty narrow band sources, right? If you wanted to make something that covers like the C-band, like an entire, a C-band type source, you do it with an array of these nano lasers, correct?
I could.
Have you tried putting a bunch of them together and see how they
No, not yet.
interact?
We just in embryonic state at this point in time. We just demonstrated lasing action maybe 3 months ago. But the idea is, you're entirely right, to make possible to build arrays of them on the same chip. Once I can control, in fact, would be nice to log them together, that when the temperature changes, the comb of frequencies is floating all together, not one independent of the other. Then the detection process on the receiver would be significantly simplified. You don't need to control temperature at all. You just put few photodetectors extra in the demultiplexer. So.
Any questions?
One other question about the micro lasers is the micro laser fabrication a CMOS compatible process?
No. We succeeded to integrate InGaAsP layer to silicon layer. I didn't show the result because there's nothing to show. We just integrated InGaAsP on silicon and etched the InGaAsP with chemistry to etch InGaAsP and not touch silicon. So basically it sits on silicon wafer, silicon slab. We have bumps of gain media. So it is, I don't think it is CMOS compatible, but I don't want to predict the future. If it will be a viable technology, maybe the process can be somehow modified to incorporate integration of 3/5s if it's absolutely necessary. Didn't happen so far.
Okay. More questions? I have one, but I'll ask you later. So we can finish on time. Let's thank Shai again.